so we're continuing on now with homework number 4, and this is problem 2 in statics. So we have this flagpole, and it's got some guide wires, and these cables are here. They're connected at point A, and the cable between A and B has a tension of 250 pounds, whereas the cable between A and C has 350 pounds. And the dimensions here are 10 feet, 7 feet. So let's see, the X, there's 10 feet right here. Here's 7 feet. Here is 6 feet. And here is 9 feet, and then this thing is 25 feet. And we want to find the resultant vector of these forces acting on point A, and we want to now we want to like estimate the direction of the wind is blowing if X is in the east and Z is in the south. So this is sort of like a bonus question, really, on one level. I just wanted to see what you get. I might tell the grader, like, just want to make you think about the directions of things that are going right here. If you had a resultant that was going in that direction, what direction do you think the wind is going in? It isn't necessarily going to be exact, because some things are going on with the statics. Like the flagpole will support some stuff, but you get kind of an indication that the wind is sort of blowing in a particular direction because of which way the resultants are going. So I want to make you think. Okay, so let's see. We'll write this one up and get started here. I'm afraid I had a little technical difficulties with the previous one. I'm not sure. I might have to redo it, which is really, I really don't like that. I might just post me reading through the problem, but I did record it, but then as it was loading up, it didn't seem to be loading correctly. I don't know. I think I might have had a glitch. Alright, so this is Spring 21, and this is what class? ES110, and homework 4. And problem 2, and you know, some professors just post stuff from their from the solution manual, you know that, and I try. I don't think that's the right thing to do, so I'm trying to be better than that. Do you care? I don't know, maybe not. You'd rather just have it, life would be a little easier, right? If I would care less, your life would be easier. Is that true? I hope you don't think that. I'm doing this because I think you will benefit from it. Hope so, at least. All right, there you go. And the connection point is like right up here, so we're going to draw it like right over there, which is kind of, unfortunately, it's in line with that a little bit more than you'd want, but I think we'll be able to read it, what's taking place right there. Yeah. So I keep bending my paper here. Here is A, here's B, and here is C. We don't need some of these lines to be that long. Here's the positive X, Z, and Y. I can draw him up here. Alright, so here is my ZOC, and of course that's O. And this is XOC, and this is XOB. Over here is ZOB. And then I guess I'll put it right next to this thing right here, ZOA. Good enough. And given the we know that the force in AB, so I'll go FAB, but I'm not going to make it a vector because I'm not going to show what direction it is. It's just the magnitude. We might even like go magnitude like that right there, and that's going to be 250 pounds. And then in AC, it's going to be 350 pounds. That's the tension in that cable, and then in that cable. And then the dimensions XOB 10 feet. I'll put these next to each other. ZOB, 7 feet. And then we have XOC, 6 feet. And then ZOC, 9 feet. And then lastly, YOA, 25 feet. And we want to find the resultant that's taking place at A. Or maybe I should just write it out. I don't know. Resultants and reactions. Sometimes they end up with the same symbol, so I'm kind of second guessing this. But I should write this as part A anyway. We can find resultant at A. That's good enough. And B, direction of wind. And we don't necessarily know that the wind is going in that direction, because even without a wind, we could have placed tension onto this flagpole. So this is not really, I don't know, it's not really close to reality. But at this point right here, you could probably, you'll probably be okay. But I'm going to point out to you that this flagpole could have been up here without any cables on it. So it just because it's cantilevered right here, this thing could support the bending moment that would be created at the base of the thing could support the wind. And then even without a wind, we could put that the cables into that tension right there. But we can get kind of a guess, like if the cables were a little bit loose, maybe not exactly loose, but maybe they were just not so tight, and then all of a sudden the wind's going, so we can kind of guess. I think it's a bad question. I did this with another problem where I did it with a hot air balloon, and then it would have been true. But here it's kind of shaky. I thought because of the flag. That made me think of it. But anyway, let's see what happens. Okay, so for my cable, for cable AB, we're going to find the direction cosine. So we're going to find we'll take the dx is going to be, well, everything here in this case is going to start from A, right, and go to B. Go to A and go to B in this case. Then in the next one we'll go from A and to go to C. So these dx's, I'm not going to give these subscripts because I'll just restart when I go to the next one. So in the x direction on B, we're going in the negative XO. So we have negative XO, right? So it's going to be negative 10 feet. And the dy, we're going downwards, right? So that's going to be negative 25 feet. And then in the z direction, we're actually going positive. So dz is, for B, is going to go 7 feet. So the DAB, if you will, and I could have gone like ABX, ABY, ABZ right here, is going to be our negative 10 squared plus negative 25 squared plus 7 squared. Right, so let me write that down. Let's see, 10 squared, 25 squared, add that, 7 squared, add it, take the square root. I get it's going to be 27.82 feet. So the force in cable FAB, I'll go FAB, is going to be equal to, and I'll go in here 250 times negative 10 divided by 27.82. It's going to be I, and then we go 250. Going to go negative 25, 27.82 J, and then 250, 27.82. Let's see. Can I get it fit over there? I don't think so. So 250. I have negative. I can't see that. 89.86. 250, 25, 27.82 divided, I got negative 224.7 J, and then 257 and 27.82. I get a 62.90 K. I hope I did that right. So you can see how we distribute. Now we go cable AC, and maybe I want to fix this up here. Yeah. I think I can fit that in there. Maybe it's just good practice, right? We'll go ABX, ABY, and ABZ. Then we go ACX. Well, we know that's going to be in the positive X direction here, right? That's and it's 6 feet. DACY is also that negative 25 feet, and then the DACZ is also positive 9 feet. So our distance AC is the square root of 6 squared plus negative 25 squared plus 9 squared. And 36, 25, 81. All right, so we have 27.24 feet. So they're kind of close in length, weren't they? Now we have the FAC. We will take our 350. And it's going to be 6 feet, right? 6 feet. And divide by 27.24 I, and then 350 times our negative 25, and we have 27.24 J, and then 350 and 9, 27.424. Okay. Whoop, I'll put it down to the next line because it's too close. 350, 6 times 27.24 divided. We have 77.09 I plus 350 25 times 27.24 divided. We'll have negative 321.2 J, and then 359 times and 27.24 divided. We'll have 115.6 K, and these are pounds. So if we have the resultant is going to be FAB plus FAC, right? So that's going to be negative 89.86 plus 77.09 I, and negative 224.7, negative 321.2 J. I'm going to have to squeeze this. I hate squeezing it in, but didn't plan it out too well here. Let's see, 62.90 plus 115.6. Okay, and those are pounds, right? The whole thing. So our resultant, that's going to be our answer right here. And we might say this is the resultant at A. I guess I'll call it the resultant at A. Resultant at A is going to be, let's see, that's 89.86. It's negative, right? And 77. So you can't see my wonderful calculator screen, can you? Okay. 0.09, add them together. It's going to be a negative 12.77 I plus we have 224.7 and 321.2, and that's going to be a total negative 545.9 J, and then 62.9 and 115.6, and they both add together, so we get 178.5 right there, right, and K, and this is pounds. Now I think I'm going to go ahead and just say here's my answer right here, because I don't want to rewrite it out again. Now for that last part right here, the only thing, you know, we'll try to think our way through this. This is pointing downwards, so this one means that it is pointing in the negative x direction, right there, right? So this one is pulling more than this one, so the wind must be going. No, wait a minute. Let me say this again. Oof, jeez. Oof, wait a minute. Yeah, this is counterintuitive, right? Because this guy is pulling more in that direction. This guy's pulling more in that direction than this one is. That's interesting, right? I'm going to check that number right there. Yeah, let's check that number. I'm a little questioning there. Yep. Okay. No. Okay. So it's true. All right. This is the kind of engineering thought that we have to go through, trying to check and see if when you're trying to make sense out of a problem, you kind of have like a little argument with yourself, if you will. Don't let anyone catch you talking to yourself, or record it in video, and then they just think you're making a video, right? So anyway, it is pulling in the negative x direction. So we are thinking that the wind must be blowing in the positive x direction to cause that, right? And then the same thing is true here. This thing is pulling in the positive z direction, so the wind must be blowing in the negative, right? So the wind is blowing to the north and to the east, right? So right here is our east, and here is our north. Whoops, right there. And so and we're going to assume that like this is an indication of the wind blowing, right? That maybe the thing, they were tight, just barely like slack, just barely slack, right? And then the wind is the entire thing that's causing this, right? But even then it's okay. This is just a thought experiment right now. I thought this would be like insightful right here. Maybe I was wrong. But anyway, we're going to be going more in the north direction, right, than in the east direction, because there's very little in the east. So what we want to do, if we're going to have an angle right there, most of the time for these right here, we would report them by way of the smaller angle, right? So we would say that we would be going, we might actually be coming in here, and I would say maybe I'll call that beta or something, and this would be east of north, as opposed to going, what I'm throwing here right now, this would be north of east, right? But anyway, that angle that we would find right there would be the inverse tangent of rise over run, so it would be 178.5 divided by 12.77. So that's going to be quite the large angle I'm predicting. It was a good. It was all in good intent right here. So that ends up being 85.91 degrees, or as I've drawn right here, So that's going to be 90 minus that, or simply 4.09 degrees, 92 degrees. Okay, so part B is 4.09 degrees east of north, which is probably more typical right here, or you could say that it was 85.9 degrees north of east. The best laid intentions, you know, just trying to get you to think a little bit also, you know. Yeah. I'm not going to give you a hard time for not getting this right, because there is a certain amount of expectation that you wouldn't know how to approach it, but it's also, I don't think it's technically 100% right. Let's see if this video will work. I hope the other video worked. I don't want to go back and fix it.